Dimensional analysis is a powerful method used to verify equations, derive relationships, and convert units, all using the dimensional formula of physical quantities. It helps us answer, is this equation logically correct? Can I estimate a formula if I don't know it yet? Let's explore how dimensions help us make sense of the physical world. At the heart of dimensional analysis is the principle of dimensional homogeneity. It states that each term in a physically valid equation must have the same dimensions. Example, in the equation for distance, x equals x naught plus v naught multiplied by t plus 1/2 a multiplied by t squared. Let's check the dimensions. X and x naught equals length L. V naught times t equals L times t to the power minus 1 times t equals L. A times t to the power minus 2 times t squared equals L. All terms have the dimension of length. The equation is dimensionally consistent. Let's test a common formula. Force equals mass times acceleration. Mass equals m. Acceleration L times t to the power minus 2. Force equals m times L times t to the power minus 2. Dimensions match both sides. The equation is valid. What about this one? Kinetic energy equals mass times velocity squared. M times L times t to the power minus 1 squared equals m times L squared times t to the power minus 2. Also valid. Dimensional analysis is used to check the correctness of equations, derive unknown relationships between quantities, convert units from one system to another, predict formulas when the physical dependencies are known. Although we can't find exact constants like 1/2 or pi using this method, we can find the general form of a formula. Dimensional analysis has its limits. It can't determine dimensionless constants like 1/2, 2 pi, or e. It can't analyze equations with trigonometric or logarithmic functions. It can't distinguish between two quantities with the same dimensions, like torque and energy. So while it's a strong checking tool, it's not a replacement for proper derivation or experimentation.